We now jump into the topic of sequences, and later we'll see series, and this will become a really major theme and topic for our second half of Calculus 2. And up until now, we've looked mostly at continuous functions. For example, these guys here, these are continuous functions. That didn't look continuous. There we go. And we were summing up areas and using integrals to find like area between curves. And we now apply the ideas of limits and infinite processes. Both of these were very important in integrals and in these functions that we looked at here. We were looking at limits and that infinite process of summing up a bunch of, beginning to be infinitely thin little rectangles. But these ideas we're going to take and transfer to discrete situations now. So not continuous functions anymore, but discrete situations. So something that looks more like this, where we don't have this continuum of values, but we're looking at very discrete, isolated points. And the first place that we're going to start looking is this is essentially a sequence. So a sequence is a list of numbers written in a definite order. Okay, so a sequence is a list of numbers that are written in a definite order. So it's not just like a grab bag of a bunch of numbers. It's numbers that come in a particular order, and they don't always, but oftentimes there's a pattern to them. You don't have to have a pattern to have a sequence, but the ones that we'll look at almost always do. So for example, this would be a sequence: 1, 1/2, 1/3, 1/4, 1/5, and so on. And we call the nth term of a sequence an, so we can imagine it just going on forever and ever. This is a1, the first term, a2 is the second term, a3 is the third term, and you can probably pretty quickly see the pattern for this. An will just equal 1 over n. In this case, this is how this sequence is defined. I want to look at a few sequences, and we'll talk about the idea of converging and diverging sequences. So this sequence is defined as n over n plus 1, and I put these curly brackets to indicate that it's a set, a set of numbers, and we'll start with n equals 1 and we'll go up to infinity. So we have an infinite set of numbers. So this is the sequence. If we were to lay them all out, it would be 1 over 2, so 1/2, and then we just go up to the next n. So 2 over 3, and let n equal 3, we get 3 over 4, 4 over 5. It keeps going on infinitely. So if we were going to graph this sequence, this is what it would look like, at least in the beginning. That first term was 1/2, and the second term was 2/3. The third term was 3/4. These never get connected because it is a sequence, so they are just discrete points out there. But we can just graphically and visually see what they're converging to. All of them are getting closer and closer to the number 1. So we will say that this sequence converges to 1. We can tell this graphically. But you can also look at kind of algebraically what's happening. You'll never be over 1. This series could never have a term that is 1 or greater than 1, and yet you're getting closer and closer to it each time. We'll look at another sequence. We'll have, -1 to the n times n plus 1 in the numerator, and then 3 to the n. So just slightly more complicated, still pretty easygoing. And so if we wanted to think of what the terms of this sequence would look like, it would be the set, let's see, if n equals 1, we have a -2 over 3 to the 1, that's 3. And then if n equals 2, -1 squared. So often you'll see this -1 to an n or to an n minus 1. It's just allowing the sequence to alternate between positive and negative values. So when n equals 2, this will just all be positive. So we have 2 plus 1 is 3, and then 3 to the second power is 9. The third term of this sequence would be -1 to the third, so we get our negative, and then 3 plus 1 is 4 over 3 to the third, which is 27. Oops, got to get my negative to the 27. The next term will be 5 over 81. It'll be positive, and it keeps going on and on. So each term is alternating between negative and positive. The numerators are all just powers of 3, and then this is just whatever number term it is, plus 1 in absolute value. So we have to think, I wonder if this sequence converges or diverges. So let's take a look at its graph. So this is at least part of the graph of this sequence here, and this horizontal line right here is x equals 0, but we're looking at values, actually n equals 0 is really technically correct. We're looking at values where n is 15, 20, 25, 30, 35. And these numbers, I don't know if you can tell, but they're very tiny numbers, which makes sense because these numbers are getting tinier and tinier. These powers of 3 are really going to start dominating. They're going to become very large numbers. And these numbers in the numerator are just plain old counting numbers, like we're just going up 2, 3, 4, 5. And even though they're alternating between positive and negative, they're both zeroing in on the value 0 or y equals 0 here. So this sequence also converges, and it converges to 0. It does it in an alternating way where it's going up, down, up, down, up, down, but it slowly gets closer and closer to 0. So this, we will say, converges to 0. Definitely not all sequences converge to a fixed value, and so we have to recognize that, of course, not all sequences converge. You can probably pretty quickly think of an example of a non-convergent sequence. You could think of the sequence 1, 2, 3, 4, 5, just counting numbers. This does not converge. It just keeps getting bigger and bigger. And when a sequence doesn't converge, we say it diverges or is divergent. One important thing, we'll look at several examples. You don't have to be going off to infinity to not converge. You can still be sort of bounded, but still not converge. And we'll want to look at some examples of how that's even possible. But this idea that there are some sequences that will converge to a certain value and some sequences that won't is very important. In this example, we're given the sequence and we're asked to find a formula for the general term of the sequence. So sort of going backwards, like putting this back in the package, seeing if we can describe the general term an with a closed equation or closed formula. So to find the general term, we just have to sort of look and see what's going on here. We have in the denominator, we can, wait a minute, this should be 625 here. We can see that these are powers of 5 going up and up and up. So that should be no problem. This will be like 5 to the first, 5 squared, 5 to the third, 5 to the fourth, etc. We have some sort of alternating, so positive, negative, positive, negative, positive. So we'll have to account for that. And then we start with 3, but then we just go up by 1 each time. So we'll take a stab at this. The general term should be 5 to, it really is the nth power because 5 to the first, 5 squared, 5 to the third, 5 to the fourth. So it is 5 to the nth. Let's see if we can figure out how to deal with the positive negative. If we do just negative 1 to the n, this will not work because if n is 1, that means this should be negative, but our first term is actually positive. So the way that we can remedy that is we can either say n minus 1 or n plus 1, and then we'll get the right positive negative. So here when n equals 1, this is 0. Anything to the 0 is just 1, so that works. If n was 2, this would be negative 1 to the 1. That gets us our negative. So this is the right start to our general term. Okay, we got that part, we got this part. Now we got to figure out what's going on in the top. We have to account for this 3, 4, 5, 6, 7, but the 3 needs to be the first term. So how about something like n plus 2? Then when n is 1, we get our 3. When n is 2, we get our 4. When n is 3, we get our 5. That seems to work. So this looks like it should be the right general term for this sequence. So we now turn to a pretty important topic, which we hinted at before and talked a little bit about before, the idea of sequences converging or diverging and figuring out when that happens and if they converge, what they're converging to. So we need to start with the definition of, for sequences, what converging really means. So a sequence converges if there exists an L. Okay, so I don't know if you guys know this, but this is shorthand for there exists. I should have written that out probably. If there exists, it's just a math shorthand, an L such that we can make an, so our, one of our terms, as close to L as we want if we take n sufficiently large. So this is often written the limit as n goes to infinity of a sub n equals L. Very similar to continuous functions, but we're keeping in mind that these are discrete functions. These are actually just sequences of numbers that are trying to, or not trying very hard, to converge to a certain number. So the key is that we can make it get as close as we want. This close, as long as we take a big enough n. There will be sequences that do this and sequences that don't. So let's look at 3 examples of sequences that do not do this, that won't follow this converging definition. So we're going to look at examples or non-examples, sequences that are not converging, they're diverging. And of course, this is one of the most basic ones where the sequence just is going off on its own up to infinity. It's never going to get close to one particular number. It's just keeps growing infinitely large. So this is definitely a divergent sequence here. This is actually another example of a sequence that does not converge. It's divergent, and it's not like it's going off and becoming infinitely large. In fact, it's very bounded. It never gets bigger and smaller than what you see here. It's always kind of turning around and staying within its zone, but it is not converging to any one particular number. So I can't say, maybe this is the limit here or this is the limit here. No number can be a limit because I can never make, what we want to do essentially is guarantee that after a certain point, after this certain number n, all of the values will be as close as I want. I just want them this close. I get to pick any value. And that never happens in this sequence because they're always just, getting large, getting small, getting large, getting small. They're never hovering in around one number. So this one is divergent. This is a third example of a sequence that diverges. Even though most of the terms are acting pretty nice and trying to get closer and closer to 5 here, every now and then we get one that pops up and is at the value 6. And so we could never guarantee that we could get a certain amount of closeness if we, just take n large enough, because forever after we're just going to get maybe a random one that's popping up to 6. And so we say that this sequence diverges. Even though most of them are acting like they want to get closer to 5, these random ones that are popping up to 6 and will forever are messing it up for everybody. Okay, so here are our 3 examples of divergent sequences. We'll see both. We'll see convergent sequences and divergent sequences, and we'll have to determine, based on some information, whether a sequence converges or diverges. Okay, we're being asked to determine if the following sequence converges or diverges, and this is our guy right here. I can't tell initially just by looking at it. Well, I can because I see a lot of sequences. I've done this for a long time, but I can tell whether it is. But typically we can't really look at a sequence and say, oh, this diverges or this converges. Sometimes you can, sometimes you can't. So the very first thing I'm going to do is I'm going to just get a feel for this sequence by listing out some terms. So I know A1 is going to be 3 plus 5, so that's 8. Over 1 plus 1 is 2, so A1 is 4. And A2 would be 3 plus 5 times 2 squared over 2 plus 4, which is 6. So that's 23 sixths. A3 would be 3 plus 5 times 3 squared, so that's 45. Over 3 plus 9, which is 12. This is 48 twelfths. No obvious pattern. I mean, we see this pattern, obviously, but I can't tell exactly, just based off these numbers, if they're going to just keep getting bigger and bigger or if they're going to start converging to something. So we have, so far, just the sequence is 4, 23 sixths, 48 twelfths, and I could keep going. I could keep getting terms. And just by doing that, I might be able to tell if it's converging to something just by listing a bunch of terms. But there's other ways we can tell too. Let's look at this kind of algebraically and see if we can determine some things. And then we'll look at it graphically as well. So algebraically, if I have 3 plus 5 n squared over n plus n squared, and you've probably seen this trick done before, where what if we divide everything by, you look at the highest power and divide everything by that highest power, so 1 over n squared, and just so that we're essentially multiplying by 1, we take the numerator and denominator and multiply it by 1 over n squared, and so this would be 3 over n squared plus 5 in the numerator, and we would get 1 over n plus 1 in the denominator. And we're really interested in, as n gets bigger and bigger, what this is going to look like. And this is, as n gets bigger and bigger, these terms, this guy goes to 0, this guy goes to 0, this guy stays constant, this guy stays constant. So it looks like, if I had to guess, I'd say that the limit of this sequence is the number 5. But let's take a look at it graphically also. So this is pretty strong evidence that our sequence does converge to the number 5, but we're going to look at it graphically also. Okay, in your homework assignment, you'll see a link to this Desmos graph. This is a specific way that you can code into Desmos sequences instead of just continuous functions. And so we're going to put in, and Desmos really likes x instead of n, so we're going to use x. But our sequence should look, let's see, x plus x squared. Okay, awesome. So, okay, this sequence, yeah, graphically we can see, I'm going to open up the tool. I'm going to change the x and y axis. So y-axis, I'm interested in it going maybe to 85. No, not y. Up to 7. And the x-axis will go to 85. And we're not really interested in negative n values. Okay, so this is what the sequence is doing. And so I've graphed the sequence. This is an interesting sequence because it does go, it starts at 4 and then dips down, but then closer and closer to 5. There's no funny business going on here. All of the terms really are trying to get closer to 5. So that formal definition of a limit is working. If we wanted to get within 1/1000th of 5, we could do that just by picking an n sufficiently large. So all of those requirements for there to be a limit are exhibited here. So now we can see graphically as well as algebraically that the limit of this convergent sequence is 5. So this is the value, let's see, let's get a better color. This is the value of 5 right here. And the sequence is definitely converging to that value. Okay, so we say that this converges to 5. So I want to end with some context. Why are we even talking about sequences? Why are we learning sequences? And soon we'll learn the next step, which is called series, where you add up a sequence. Why are we learning sequences and series? And so I wanted to give you some perspective on this. We kind of hinted at it at the beginning of the video, but I wanted to give you a more detailed explanation for this. I promise that this work with sequences and series will be very valuable. It's very applicable to many contexts in real life. But the first answer I guess I would give is what I talked about at the beginning, that we're extending the ideas of limits and infinite processes that we've already learned in integrals to these discrete sequences. And there will be some important applications there. So probably one of the most powerful applications that we'll see are what are called Taylor series. So this is one of the most powerful applications that we'll see. And the basic idea is sometimes we come across continuous functions that are very difficult to work with. A Taylor series is a way to approximate a complicated continuous function as infinite sums of polynomials, so this infinite series. You think of polynomials like 3x squared plus 4x plus 5. Something like that is so easy to integrate, right? And so easy to work with. So polynomials are like the building blocks of functions, and maybe not the building blocks, but the simplest types of functions that we ever come across. And so if we could have a way to take a very complicated function that's very difficult to work with and maybe mask it or approximate it as a polynomial and then work with that polynomial, that would be a really powerful tool, because then we could do a whole lot of things that we can do with polynomials that maybe we weren't able to do with this really complicated function. So Taylor series, which will be, we're going to next be talking about series, and Taylor series is a method to enable us to do this. It's a really super powerful tool. And maybe one way that I'll say this, we haven't even talked about series yet, and I keep bringing it up. Series are just where you take a sequence and you're adding up all the terms. And the series are kind of like the discrete equivalent to integrals. So where you had an integral where you were summing up continuous slices. In a series where we're adding up these sequences, these infinite sequences, this is where we're summing up discrete terms instead of a continuous slice. So summing discrete terms. And maybe just the last thing I want to say, let's make some, is that series are going to extend the ideas of accumulation and approximation. Two huge ideas with integrals, and we're going to use those ideas in these discrete contexts.